Segment bending. Techniques 16. Now that the procedure to lay out the conduit with bending marks is understood, the next step is bending the conduit using a hydraulic bender. As segment bending requires several small angle bends to complete a 90-degree stub, some method to measure the amount of bend in degrees will be required. Determining the degree of bend can be done basically 4 ways. 1. Greenlee bending degree protractor. The Greenlee bending degree protractor hooks onto the pipe being bent using a spring and chain assembly. The circular face of the protractor is divided into 4 sections. The sections are marked in increments of 18, 20, 21, and 30 as shown in figure 16:1. Step 1. The bender frame is in the upright position and the pipe is leveled as shown in figure 16:2. Once the conduit is secured in the bender and the bender shoe center mark is on the first bend mark, not the start mark, the face of the protractor is rotated to the segment that corresponds to the number of bends, shots, being used. The scale is then, adjusted so the pointer is on 0. Step 2. The pipe is then bent using the hydraulic pump until the pointer reaches the first mark. Bend a little past to compensate for spring back *. Release the pressure and check the pointer. Spring back is a term used to describe the amount a bent pipe tends to straighten after the bending force is removed. Only a few bends will be needed and you will find just how much you must bend past the mark, over bend, to compensate for spring back. Care must be taken with each bend, as a small error multiplied 20 or 30 times is a large error. Step 3. The pipe is moved forward in the bender to the second bend mark and bent until the pointer reaches the second mark on the protractor face. Again bend past the mark to compensate for spring back. Step 4. The conduit is moved to the third bending mark and the pipe is bent so the pointer is at the third mark, again over bending to allow for spring back. This procedure is followed at each bend mark until the 90 degrees stub has been achieved. Note: it is a good idea to check the developing stub length before the last few bends are made. Make spacing corrections as required. Shorten spacing if stub is coming up long, lengthen spacing if stub is coming up short. If the stub length is reached before the pipe is at 90 degrees or plumb, don't bend any of the remaining bend marks. Move the pipe in the bender and bend at the start mark to get to 90 degrees. This brings the pipe to plumb without adding to the stub length. 2. Magnetic angle finder. The pipe must be kept level and the bender frame must be upright as shown in figure 16:3. When a magnetic angle finder is used, as with the bending protractor, care must be taken with each bend to eliminate errors. Step 1. Level the conduit and place the magnetic base angle finder on the stub end of the conduit. The angle finder will indicate the degree of each bend as determined by the number of shots you are using, i.e. for 20 shots each bend would be 4.5 degrees. Step 2. Pipe is bent until the angle finder indicates just past the desired degree of bend to compensate for spring back. If the right amount of overbend was made, the angle finder should read the desired angle of bend. If you overbend too much at one of the bend marks, you can compensate by underbending at the next mark. In 2 or 3 bends you will find just the right amount of overbend to allow for spring back. Step 3. If the first bend was a 4.5 degrees bend, the next bend will move the pointer on the angle finder to 9 degrees. The third bend will be completed when the pointer is at 13.5 degrees and so on until the 90 degrees bend is completed. Note: as with the bending degree protractor, check the developing stub length before bending the last few bends so you can adjust the spacing or degree of bend as required. 3. Amount of travel method. With this method the pipe can be bent in any position without the pipe having to be level. This method is very similar to the amount of travel method discussed in the Chicago Bending Chapter 13. It varies only in the method in which the travel figures are found. To find the amount of theoretical travel for a 90 degrees bend, proceed as follows. Step 1. Set up the bender with the pivot shoes in the proper holes for the conduit size that is to be bent. Step 2. Measure the distance, d, center to center between the pivot shoe pins as shown in figure 16:4. The plunger, also called the ram, will have to travel half this distance to bend a fill 90 degrees stub as shown in figure 16:5. The travel required per shot then is 1/2 the distance from pin to pin divided by the number of shots. Example: the distance from the center of the pins is 24, and the pipe is to be bent in 18 shots. Travel per shot equals 1/2 the distance from center of pins, which is 12 inches, divided by the number of shots, which is 18. Travel per shot equals 12 divided by 18. Travel per shot is 0.666. 0.666 is between and 11/16. To make the measurements easier, measure heavy plus or measure 11/16 light. Bending using this method will follow a different procedure. Step 1. The center of the bending shoe is placed on the first bending mark, not the start mark, and the hydraulic pump is activated until plus of ram travel is measured as shown in figure 16-6. Do not allow for spring back with this method. Rule is placed on bender shoe and travel read at any convenient reference point. Step 2. The pipe is moved to the next bend mark and the pump is activated until another 5/8 plus of ram travel has been measured. Continue to move the pipe and measure ram travel. As you approach the last few bending marks, 4 or 5, check both the developing stub length and the angle of bend. Spacing and/or amount of travel can be adjusted on the last marks to bring the stub on the money, or for final truing. Note: once you have found the amount of travel for 90 degrees, we can also find the amount of travel for any other angle for offsets, kicks, etc. Divide amount of travel by 90 and multiply the answer by the desired angle of bend. Example: if 90 degrees travel is 12 inches, what is the travel for 22.5 degrees? 12 inches divided by 90 equals 0.1333. 1333 by 22.5 equals 2.999, or 3 inches of ram travel. 4. Number of pumps method. With this method the pipe and bender can be in any position. This method depends on the idea that a given number of pumps on a manual hydraulic pump will produce the same amount of travel each time. This method may work well today, but next week the same number of pumps may not produce the same amount of travel. The change in travel is caused by a change in fluid level, a ring condition, and the condition of the pump. Example: using the one-shot shoe, not the segment shoe, and a manual hydraulic pump, count each pump until a full 90 degrees bend has been achieved. If it takes 40 pumps to bend a 90 degrees stub, it should only take 20 pumps to achieve a 45 degrees bend, 10 pumps for 22.5 degrees, 2 pumps for a 4.5 degrees, etc. As you can see, this method should work very well, but will require additional time to determine pump degree values. But the extra time initially is offset by not having to measure ram travel at each bend mark as required by the amount of travel method. Use the same procedure for bending as outlined in amount of travel method. Check developing stub length and degree of bend prior to bending the last few shots. Use the remaining shots for final adjustments in stub length and truing the 90 degrees bend. Note: use any of one of the 4 methods that is most convenient, but remember that extreme care and attention to details is required for each method. A small amount of error at each bend will compound itself and accuracy in BC ending will be impossible to achieve. To make hydraulic bending easier, a bending table, either a commercial model, Greenlee 1802 bending table, as shown in figure 16-7, or ONC constructed on the job site. The table will hold the conduit and the bender, making leveling and plumbing easier and produce more accurate bends. The table will also eliminate the need to continually wrestle the conduit and the bender. In the event a table is not available or impractical due to job conditions, an indispensable bending aid is the wow watcher, or no dog, as shown in figure 16-8. The wow watcher is attached to the end of the conduit and is used for leveling and/or alignment to eliminate wows and dog legs as the conduit is moved in the bender. The wow watcher is also an indispensable tool when bending offsets, saddles, and other multiple bend pipe jobs. The wow watcher is made of Vertron, a space-age material that produces a lightweight but strong tool. The tool uses a straight bubble vial so it can accurately indicate level in more than one plane or position. You can order a wow watcher at www.coxco.net. Figures 16-9A and 16-9B show how a leveling device can easily be fabricated on the job by welding a piece of angle iron to a coupling if you don't have a wow watcher. If no welder is available, an alternate method is to clamp uni stud onto the conduit as shown in figures 16-10A and B for a base for your level. Although not as mechanically sound, a hacksaw blade and a coupling may be used as shown in figures 16-11A and B. Saw a slot across the coupling and insert a saw blade. The slot is then peened to yield the blade fast. Segment offsets. To bend offsets or any other bend of less than 90 degrees will require little new information. We will need to determine the radius, find the developed length and spacing between bend marks, much the same way we did for 90 degrees stubs. The formula we use if the bend is less than 90 degrees is: developed length for less than 90 degrees equals radius x degree of bend by 0.0175. Asterisk 0.0175 is 1.57 divided by 90. Example: find the developed length for a 30 degrees bend with a 20 inches radius. Radius, 20, x degree of bend, 30 degrees, Vi.0175 equals 10.5, develop length. Next we need to determine spacing. Remember the rule for smooth bends, not less than 3 degrees nor more than 6 degrees bends. Let's do this job using 5 degrees bends. It will take 6 bends of 5 degrees to make our 30 degrees bend. 6 times 5 degrees equals 30 degrees. Develop length divided by number of shots, 6, equals 1.75. Spacing is shown in figure 16 to 13. Example. Consider a typical offset bending job, an 8 inches offset in a 3 inches pipe. 1. Determine the spacing radius. If space is no problem, 8 times the trade size of the conduit would be 24. Radius 8 by 3 equals 24. 2. Determine the angle of offset to use. If space is not a problem, smaller bends make easier wire pulling. Let's use 20 degrees bends. 3. Find the developed length, dl, radius, 24, x degree of bend, 20 degrees, Vi.0175 equals 8.4 inches dl. 4. Number of bends, shots, for smoothness of bend, use 4 degrees bends. 5 shots will give us 20 degrees offset bends. 5. Spacing between shots equals dl divided by shots 8.4 inches divided by 5 equals 1.68, or equals 1 and a 16th, rounded to the nearest 1/16. For accuracy we will round to the nearest 16th of an inch bend spacing measurements. 6. Spacing between offset bends. Height of the obstruction was 8 inches by 2.92, offset multiplier for 20 degrees, equals 23.39 or equals 23/3/8. Between the bend A and B7. Layout pipe and bend is shown in figure 16 to 14. It should be noted at this point that all multipliers and shrink values listed and discussed earlier in the text may be applied to segment bending regardless of pipe size. Bending offsets of more than 30 degrees and larger than normal radius, the pipe may end up too long when shrink is used and the pipe is cut and threaded before bending. This is caused by gain in the two offset bends. Although correction factors will depend on the equipment being used, Table 16 to 15 should be close enough for most equipment. To apply the correction factor, locate the correction factor under the angle of offset bend. Multiply this value times the radius of bend. The answer, product, is deducted from the total pipe length after all other standard calculations have been made. Example. Using the offset as shown in figure 16 to 16, find total shrink, height of obstruction, 18 by 3/8 equals 6 3/8. Total pipe length. Total dimension, 102, plus shrink, 6 3/8, equals 108 3/4. Under the 45 degrees column is listed a correction factor of 0.0430. This value, 0.0430, is multiplied by the radius of the bend, 15. 0.0430 by 15 inches equals 0.654 or equals 5/8. A correction factor of is subtracted from the total pipe length. 108 3/4 equals 108 1/8 for the adjusted total pipe length as shown in figure 16 to 16. This correction factor as indicated is very general and may have to be adjusted up or down as you find necessary. Segment saddles. Regular saddles will be bent as outlined earlier in the text. A saddle is simply two offsets, so using the previous information and that just covered in segment offsets, bending hydraulically should pose no problem. The 3-bend saddle bent hydraulically must be changed a bit and bend as two complete offsets tied together. This type of saddle is still used primarily for bridging round obstructions as shown in figure 16 to 17. The angle selected for the bends should be as small as possible to leave plenty of straight pipe between bends 1 and 2 and also between bends 3 and 4. The minimum length of straight pipe required will be determined by the distance from the center of the bending shoe to the pivot shoe. If the length is not long enough, you will take bend out of bend 1 when trying to bend at bend 2. Bends 1 and 2 are identical to bends 3 and 4, so the layout is also identical as shown in figure 16 to 18. Concentric bending 17. Concentric 90 degrees bends. Concentric is defined as having a common center or axis. Notice in figure 17 to 1 that starting from the inside pipe, each pipe has an increasing radius. Concentric pipe work requires no new layout techniques, only increasing the radius of the next pipe to maintain even spacing. The layout for concentric pipe is quite simple then. The radius of the first pipe is determined and the bend marks which were discussed earlier are laid out for a segment bent 90 degrees stub. The second radius is found by adding to the radius of the first pipe, the OD of the first pipe, and the desired spacing between pipes. Example. As shown in figure 17-2, the radius of the first pipe is 24. The OD of the first pipe is 3.5, and the spacing is 2. By adding the radius of the first pipe, 24, plus OD of the first pipe, 3.5, plus the spacing, 2 inches, between the first and second pipe, we get a value of 29.5. The value of 29.5, then, will be the radius of the second pipe as shown in figure 17-2. Once the developed length of the second radius is found, the spacing between the bend marks can be determined. Notice in figure 17-2 that the start mark for the second pipe is the same distance from the end of the pipe as the first pipe. This will be true for each additional pipe as well. The spacing will increase between bend marks as the radius of the pipes increase. This is due to the increasing developed length. All 3 pipes in figure 17-2 are 3 inches rigid pipe laid out with 15 shots. If the spacing between the bend marks becomes too wide, the radius will not appear smooth. To compensate, increase the number of shots, which will make the marks closer together and smooth out the radius. The start mark, however, must remain the same as the previous pipes. Example. Determine the concentric layout for 3 pipes. 1. Pipe will be the inside pipe and is 2 inches rigid with a stub length of 48 and a radius of 18. 2. Pipe is 3.5, rigid. 3. Pipe is 2.5, rigid. Spacing between the pipes is 2. All pipe to be bent with 20 shots. Pipe number 1, figure 17-3. Develop length, dl, equals radius, 18, times 1.57 dl equals 28.26, or equals 28.25. Spacing equals dl divided by shots. Spacing equals 28.26 inches divided by 20. Spacing equals 1.413 or equals 1 7/16, rounded to the nearest 1/16. Start mark equals stub length, radius plus OD. Start mark equals 48 inches, 18 plus 2 3/8. Start mark equals 48 inches, 20 3/8. Start mark equals 27 5/8. Pipe number 2, figure 17-4. Radius equals pipe number 1 radius plus pipe number 1 OD plus spacing. Radius equals 18 inches plus 2 3/8, plus 2. Radius equals 22 3/8. Develop length equals radius by 1.57. Develop length equals 22 3/8 by 1.57. Develop length equals 35.129, or 35 1/8. Spacing equals dl divided by shots. Spacing equals 35.125 inches divided by 20. Spacing equals 1.756 or equals 1 3/4. Stub length equals pipe number 1 stub plus spacing plus OD pipe number 2. Stub length equals 48 inches plus 2, plus 4. Stub length equals 54. Start mark equals stub length, radius plus OD. Start mark equals 54 inches, 22 3/8, plus 4. Start mark equals 54 inches, 26 3/8. Start mark equals 27 3/8. Note: start mark for pipe number 2 is the same as the start mark for pipe number 1. Pipe number 3, figure 17-5. Radius equals pipe number 2 radius plus pipe number 2 OD plus spacing. Radius equals 22 3/4, plus 4, plus 2. Radius equals 28 3/8, or 28.375. Develop length equals radius by 1.57. Develop length equals 28.375 by 1.57. Develop length equals 44.548 or 44, 1/2. Spacing equals dl divided by shots. Spacing equals 44.5 inches divided by 20. Spacing equals 2.225 or equals 2 1/4. Stub length equals pipe number 2 stub plus spacing plus OD pipe number 3. Stub length equals 54, plus 2, plus 2.875. Stub length equals 58.875, or 58 7/8. Start mark equals stub length, radius plus OD. Start mark equals 58 7/8, 28 3/8, plus 2 7/8. Start mark equals 58 7/8, 31 1/4. Start mark equals 27 5/8. Note equals start mark for pipe number 3 is the same as the start mark for pipe number 1 and number 2. Concentric offsets. Use the same procedure as with 90° stubs. Increase the radius of the second pipe, an amount equal to the radius of the first pipe, plus OD of the first pipe, plus the spacing desired between the pipes as shown in figure 17-6. This applies to ends A1 and B1. Notice, however, the ends A2 and B2 are in reverse order. This layout will be necessary if perfect fitting parallel run conduits are to be achieved. Spacing between bend marks AA and AB is found as with any offset. Desired offset height, 20, x offset multiplier for 30 degrees, 2, equals 40, between AA and AB. As the offset will be bent using two different radii, the spacing, 40 inches, must be from the center of developed length AA to center of developed length AB as shown in figure 17-7. Although the examples used to explain offset bending had several shots per bend, it should be clearly understood that fewer shots can be used. Successful offsets can be made with only 2 or 3 shots per bend. Bending parallel offsets in this manner is rewarding from a technical standpoint, but is, however, time-consuming. It is the author's contention that with offsets, 90 degrees bends, or any other segment bends, that the additional time spent bending smoother. Radius bends, more shots, is gained back when it is time to pull the wires into the completed raceway. One-shot parallel offsets. Parallel offsets of different pipe sizes can still be bent and aligned perfectly if all pipe are bent with the same one-shot shoe. This will work with 2.5, 1.5, and a quarter pipe sizes, and depending on the manufacturer and the ductility of the pipe 2.5, 2, 1.5, and 1.25, can all be bent on the same 2.5, one-shot shoe. 3 inches, 3.5, and 4 inches pipes can usually be bent on the 4 inches shoe. Again, it will depend on the ductility of the pipe, and you will just have to experiment with the different sizes of pipe and shoes to find out what will work with the equipment you are using. Intermediate metal conduit, IMC, 18. Intermediate metal conduit, or IMC for short, is a rigid steel electrical conduit that is lighter in weight than standard rigid metal conduit, RMC. It offers the same protection to conductors as rigid, but with much less weight and wall thickness. IMC has other advantages over rigid. It has a larger interior diameter, and the smoother interior of the pipe allows for easier wire pulling through the conduit. Intermediate metal conduit, as the name implies, is intermediate, between EMT and rigid. Figure 18-1 shows a comparison of wall thickness. Even with its reduced wall thickness, IMC is cut, reamed and threaded with standard pipe equipment. IMC is available in trade sizes, 1/2, 3/4, 1, 1.25, 1.5, 2, 2.5, 3, 3.5, and 4. Intermediate metal conduit is manufactured in standard lengths and is threaded on each end. The standard thread, called the National Pipe Thread, NPT, is a U.S. standard for tapered threads. Used on threaded pipes. The taper rate for all NPT threads is 1/16, 3/4 inch per foot, measured by the change of diameter of the pipe thread over distance. The threaded couplings that are used to connect or join two pieces of IMC together have no taper, or have straight threads, NPS. By not having a taper, more threads can be engaged, making for a better electrical connection, which enables the conduit to be used as an equipment grounding conductor. The thread protectors for IMC are a different color than rigid to make it easy to distinguish IMC from rigid. The thread protectors are yellow for sizes 1/2, 1.5, 2.5, and 3.5. Green is used for sizes 3/4 and 1.25, and orange is used for 1, 2, 3, and 4. NEC Article 345 governs the use and installation of IMC. Bending IMC. With the difference in OD, thinner wall thickness, and the hardness of the metal that gives it its strength, additional support must be provided to the sidewalls for successful bending larger sizes. Hand bending. 1/2, 3/4, and 1 inch trade sizes can be accomplished with hand benders that are designed to bend FMC. Hickey bending of FMC is not recommended. The design of the hickey does not give the required support to the sides of the conduit. If there is no other way available, IMC can be bent with a hickey, but it must be done with very small bites to avoid collapsing the pipe. Chicago type benders. IMC can be bent using existing rigid shoes for sizes 1/2, 1/4, and 1. Bending shoes rated for IMC and rigid can also be used for bending 1.25 and 1.5. Electric benders. Electric benders are available that will bend 1/2 through 2 inches IMC. One such bender is the Greenlee 555, often referred to as the triple nickel in the field, and one of the most popular benders is shown in figure 18-2. Hydraulic benders. Hydraulic benders can be used for bending 1/2 through 4 inches IMC. Older hydraulic benders may need conversion attachments for successful bending IMC. There are hydraulic benders designed specifically for bending IMC. A quick check on the internet will provide you with a list of equipment that will bend IMC. Rigid non-metallic conduit. RNC, 19. Rigid non-metallic conduit, RNC, is the lightest weight of all the conduits and is available in Schedule 40, Schedule 80, and Type A and are available in trade sizes 1/2 through 6. The pipe is made with polyvinyl chloride and is referred to in the field as PVC. Type A is a thin-wall rigid non-metallic conduit referred to as EPT and is listed for concrete encasement only. While Schedule 40 PVC conduit has a thicker wall thickness than Type A, it is not allowed to be used in areas of physical damage. Schedule 80 PVC conduit has the thickest wall thickness and is listed for uses in areas of physical damage. PVC is manufactured in standard 10 feet length, which includes a coupling. The coupling may be molded into the conduit when it was manufactured, as shown above, or a separate coupling is cemented, glued, to the pipe by the manufacturer. For specific applications it may be shipped in shorter or longer lengths, with or without a coupling. Bending PVC. PVC is heated and then bent. This is normally done by one of two methods. One method is to use a heat box with an electrical heating element, while the other method uses propane to heat a liquid for heating and bending the PVC. Heat box benders come in different sizes to handle all sizes of PVC. The conduit is placed in the box and slowly rotated on the rollers so heat is evenly distributed. When the pipe becomes flexible, it is removed from the box, shaped to the desired bend configuration and set, or cooled, by wiping with wet rags. Figure 19-2 shows a pipe being removed from the box after being heated. Note: the author has found that wearing standard household hot mitts, oven mitts, and dipping them in a bucket of cold water is easier and faster than using rags. The mitts allow the hands to form around the pipe, making cooling and setting the hot pipe is quicker. Bending PVC pipe 2, and larger with a heat box will require using an airtight plug in each end of the conduit as shown in figure 19-1. The plugs hold the hot expanding air inside the pipe. This heats the inside of the conduit and the expanded air make bending possible without collapsing the pipe walls. The plugs MLLST remain in place until the pipe is cooled and set. Figure 19-3 shows a box of pipe plugs. The PVC bender in figure 19-4 operates on propane gas that heats a liquid, triethylene glycol, that surrounds the pipe. The pipe is left in the heated fluid until the pipe is pliable. It is then removed from the bender, formed, figure 19-5, and the cooled to set as shown in figure 19-6. Figure 19-4, heating, courtesy Greenlee, figure 19-5, forming, courtesy Greenlee, figure 19-6, cooling, courtesy Greenlee. Another method of bending PVC is by using an electric bender blanket as illustrated in figure 19-7. The blanket is wrapped around the PVC pipe which heats it for bending. Figure 19-7, courtesy Enerpac. Note: field bends can be made with some success using a torch. Care must be exercised as the PVC will take on a brownish color if the flame is brought too close to the conduit. Placing the PVC inside a piece of larger EMT and then heating as shown in figure 19-8 helps eliminate the chance of scorching. Packing the EMT pipe with wet rags will help hold the heat in to soften the PVC quicker. Scorched pipe may be rejected by some inspection authorities.